Hey, future physicists. Today we're going to talk about wave properties. So we're starting this whole new unit on waves and sound and light. So far, we've finished the electromagnetism unit and we're moving on in the new direction. So the first thing we probably need to do is define what a wave is. It is a movement of energy in space and time. Now think all the way back to the fall when we first started studying physics. What did we define physics to be? We defined it to be the study of matter and energy, the study of matter and energy. So when we talk waves, this is going to be amazing because we're talking about moving energy from one place to another using the matter that we have or how that wave interacts with the matter. It could be either one of those methods. So wave is a movement of energy in space and time. Some other things that we want to talk about, probably some definitional type things. If we look at, we would say the medium is what the wave travels through. So if I'm playing an instrument, then the air that you hear the sound wave coming from, the air is that medium. If you look at the background of the screen here, this water wave, like the wave is traveling through the water, so the water would be the medium. So the medium is whatever the wave is traveling through. The next thing we talk about is frequency. It is how frequently you get hit by a wave or how frequently the wave is coming. And that we use it at lowercase f to symbolize that. A good way to think of it is maybe like if you're standing on the beach and the waves keep hitting you, it would be if you counted how many waves hit you in a certain amount of time. That's your frequency. So you might say, I get hit by 5 waves every second. Probably not on a beach, but you get the idea. So frequency is the number of waves per second. Number of waves really isn't a unit. And so we would say that this is 1 over seconds, and that is redefined to be the hertz, named after a dude named Hertz. You can Google him later. The next thing we would look at then is period. So what if we don't want to know how many waves we get hit by in a second? What if we want to know how many seconds it is between each wave? That's really what your period is. So it's how long each wave takes or the number of seconds per wave, which is just going to be in seconds. Now, you'll notice that this is an uppercase t. We use t to describe time. Lowercase t would be the total time, but this uppercase t would be the time for just one cycle. So it's how long it is between waves, one shot between this wave and then the next wave, how many seconds it would take for that. Then if you notice, these two are inversely related. So frequency is 1 over seconds and period is just in seconds. Or you could say cycles per second or seconds per cycle. And that's really how these are inversely related for that. So the next thing we want to talk about is the 2 different types of waves that we have. There's a transverse wave, which is a wave that if I'm going to bump this first molecule here. So if I bump the molecule, notice that that molecule goes up and down and it sends a wave through all of those dots that creates what you would typically see as a normal wave image. So the medium, the key idea to this is that the medium, remember that's what the wave is traveling through, so it's going to be all these dots that are moving, is moving perpendicular to the wave. So if you look at that, see if I can get a better color to show up on here. If you look at it, the wave started going this way, but what direction are all of those dots going? Like this first red dot, is it moving in the same direction as the wave? No, it's only going back and forth, up and down. And notice that those two are perpendicular to each other, so that the wave itself is going that way, but the medium is going up and down and they're perpendicular. The types of waves that are this would be radio waves, that you like literally pick up radio signals and you listen to 93 FM or whatever it is. Sunlight is a type of transverse wave, and liquids are also any kind of this like wave that we have. It can also be a transverse wave. So notice the direction of the wave again, just to summarize, is that way. And then the direction of the medium is that way. And if I go back, if I go back to there, so notice I bumped that first one, see how the wave is moving to the right and the dots are moving up and down. So it creates a wave that looks like this. We would say that this highest point, all of these high points are called crests. You could think of it as like the crest of a hill, you're hitting the top part. And all of these low points we would call troughs, like think of like a watering trough that a horse would drink out of. So you can think that those troughs are the low points. Now the amplitude is how far away from where the dots normally are do they get moved. So notice that they would normally be on this horizontal flat line and they get bumped all the way down to whatever the highest point of the lowest point of the trough is, or the highest point of the crest is, and that's your amplitude. So what you should not think of is it's not the height from the crest all the way down to the trough. It's only from the trough to the normal line, or from the crest down to the normal line. The wavelength then is any length of one complete cycle. So I could go crest to crest, that length would be a wavelength. I could also go trough to trough, that length would be a wavelength. Or I could go coming up into the normal here until I come back to that exact same spot where I'm coming up into the normal. That would be a wavelength also. So it's the length of one cycle from crest to crest, trough to trough, or any same point to the next same point. Tying that and frequency together, now remember at the beginning of the year, we have this equation that velocity is the displacement per time, which we can say that too. Like we could stand out on the football field. I could have one of you at one end of the football field, the other of you at the other end of the football field, and you like shout and wave your arms, and then the other person starts the stopwatch as soon as they see you move your arms, but they stop it as soon as they hear you. Then we could take the distance of the football field, divide it by how long it took for the sound wave to get all the way across the field, and see what the velocity of the wave is. Now, if we know the particulars about the wave, like the frequency, which remember is the number of cycles per second, and we know this wavelength, which is the length of the wave, we can also get the velocity that way. So those are two different ways that we can get the velocity. And think through the units. If the units for frequency are cycles or 1 over seconds, and I'm multiplying that by a wavelength, which is in meters, then don't I still end up with meters per second, which is what we measure velocity in? Yeah, isn't that awesome? Okay, now that's the first kind of wave. That's a transverse wave. The second kind of wave is a longitudinal wave. So think through, if this one has it where the wave is going to the right, but the molecules are moving up and down or perpendicular to the wave, what's our second one going to be? It's probably going to be the other way. It's where the medium moves parallel to the wave. So in this case, I'm going to bump this first one to the right, and notice that it bumps the next one, 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 and then it is oscillating. But now you'll notice that this is the same way in the red dot didn't travel all the way down. This part of it doesn't travel all the way down either. It just vibrates back and forth here. Same thing, like if you put your eye on one of these, notice how this guy here is just going back and forth here and here. That's a longitudinal wave. So the wave is going this way and the particles are oscillating back and forth in the same direction. And some examples of that would be water waves can also do that. Like if you're sitting in the tub and you push on the water, then that creates a longitudinal wave. And sound waves are longitudinal waves. So as I'm talking, my vocal cords are vibrating and pushing on the air all the way out of my mouth, all the way to the speaker. And then coming out of your speaker, those vibrations are coming and hitting your ears, and your eardrums are translating that vibration back into something that you recognize. Then your brain translates that into the sound that you hear, or the language that you hear, or the music that you hear, or whatever it is that you're listening to. So again, notice that the direction of the wave is to the right, and that the direction of the medium is left and right, or back and forth, or parallel to the direction of the wave. You will notice, and it's kind of hard to freeze the simulation here, but if you'll notice, see this group, I can't even get my pen to be it. See how there's this grouping of clusters that kind of hang together? I don't have a way to pause it. So you have this part that's moving through. Well, those clusters that are together are called compressions. And the places where we have a least amount of molecules, that would be called a rarefaction. So the molecules are rare at that point, just a way to remember it. And the molecules are compressed at this point. So you can see like right now, a compression starts moving all the way across from the simulation there. And then followed quickly behind it is a rarefaction, where there's a gapping of the molecules that you can see from that. And those are the two parts of a longitudinal wave. So your transverse wave has its crest and its trough. The longitudinal wave will have a rarefaction and a compression, where there's a lot of them together, and a rarefaction where there's a little of them together. So here we're going to talk about interference. Interference is when two waves come together and they meet. So do they cancel each other out? Do they bounce off of each other? Do they pass through each other? What happens whenever you have that happening? Well, there are two types of interference. There's a constructive interference and a destructive interference. And we're going to show you a simulation to both of those. Maybe I'll show you right after this, or maybe we'll put it at the end of the video. But it's of us moving a slinky, Mr. Claymo and I. And so he'll send a crest down one way, I'll send a crest down the other way. And you can see that when they meet, they get bigger, and then they go back to their normal, and then they keep going. And so we end up with what this picture shows. So you have this wave coming from the left, this wave coming from the right. then you'll notice that this has a certain amplitude, this has a certain amplitude. Well, the amplitudes add together to give you a bigger amplitude, and then the wave keeps going. So the wave that started out over here is still going this way, and the wave that started out over here is still going this way. Now, you wouldn't necessarily know that from the picture, but you'll see when we talk about destructive interference, it'll make sense for that. So in a constructive interference, this makes sense because things are adding up. It's constructive, it's helping, it's getting bigger. In destructive interference, it works the other way where they cancel out. So I have a crest here coming into a trough here, and if they're of the same amplitude, then right at the point that they meet, they're going to cancel out. But you'll notice that the trough is still heading to the left, like I said over here at the constructive. You wouldn't know that unless you see this one, and you'll notice that the crest is still heading to the right. So they don't bounce off of each other. They don't cancel, like they don't stop, cancel out, but they do cancel the amplitudes out, but then they keep going in their perspective ways. So destructive interference, the amplitudes of the waves pass through each other and cancel out momentarily and then keep going from that. So that's constructive and destructive interference. Some other wave properties, reflection, you should be really super familiar with. Like every time you go to the bathroom and look at yourself in the mirror, you are seeing a wave bouncing off of a barrier. So you're seeing the reflection of yourself as it bounces off of the mirror, and that's what you see in the mirror. Now, refraction is the bending of a wave when it enters a new medium. So you'll notice that in our image here, the wave is going this way, but as soon as it gets into the water, notice how it got bent down that way, that it didn't keep following that same path that it should have. That's refraction. Have you ever looked at a glass of water or a glass of lemonade with a straw in it, and it looks like the straw is totally bent away from where the bottom of the straw in the liquid is? That's refraction. It's the light bending when it enters a new medium. Diffraction is the bending of a wave around a barrier. So think through, like if I stand out in the hallway and I take and I put you all the way down and around the corner of the math hallway, and then I shout down the hall, is my voice only going to travel all the way down the hall to the cafeteria, or will it bend around the corner and that wave continue moving around the corner so that you can hear it on the end? Yeah, it's going to do that. And that's really what diffraction is. It's the bending of a wave around a barrier. Now, you don't notice it as much with a light wave because the light wave travels so much faster than a sound wave, but you do really notice it a lot with sound waves because those bend around the corner. Like literally someone could be standing right here around the corner and they'll hear, because these waves start bending around and going that way also. They don't just keep passing and skip all of that side part. So that circled part is really the beginning of the diffractions that go with that. The last thing is polarization. The last part of this is polarization. It's filtering out a part of a wave, and this is totally polarized sunglasses. So I could take my sunglasses, square is the new hip, right? So I got my polarized sunglasses, and notice that when I put them together like this, it doesn't do anything. But if I turn them like that, then it makes it totally go black. So you can see the part here where they're not overlapped and the part in the middle where I'm covering my face up. And if I turn it like that, then you can see through and see my face. That's polarization. So what's happening is light vibrates in all of these different directions. If I simplify it down to just this up and down and left and right, one of the filters is straight up and down, so it filters out all of the left and right light. Then if I take and I put my other polarized film sideways so it's horizontal, it filters out all the rest of it and none of the light gets through. And that's really what polarization is. It's filtering out some of the light. Well, why would you want that? You'd want it because maybe you want to be able to see straight ahead, but you don't want to get the glare of the sun that comes from up here or the glare that comes off of the road. You really want to only focus on a certain area. That's what your polarization does. It helps to filter out some of the light, that excess light that you don't want. Okay. Standing wave. So this one is a really, really cool one. So it's a wave that looks like it's standing still. Okay, now you can't really see it based off of the simulation here. This is a really, really slowed down version of the simulation of what it could look like. And what happens here is the reflected wave hits at the same point as the incident wave. So the incident wave would be like if I start on the left side, I send the wave all the way down to over here, and then it reflects back at the exact same point, and the wave essentially just bounces back and forth. So what I end up with, these parts where I have these bubbles, those are going to be what we would call antinodes. And the parts that are the red dots where the medium isn't moving, those are going to be called nodes. Now, one way you can remember this, and a student came up with this, I'd love to claim it, is at those red points where the nodes are, there is node displacement. Node displacement, okay? Antinodes are your bubbles. Nodes are where it doesn't move at all, okay? So that's what that is. Now, whenever we look at this, standing waves happen all of the time in nature. In fact, the other day I was outside at our setting up the track camera, and I have the field goal here. Here's the field goal. And one of these poles started vibrating so that you could see the bubble up here, the bubble in the middle, and the bubble at the bottom, because the wind was that strong and it caused it to oscillate just right. And it had this really weird hum that has certain frequency because of the harmonic that it had of those three harmonics. Those three antinodes. So harmonic is a standing wave that sounds good together. The number of the harmonic is the number of antinodes. So I would look at this picture right here, and I would say that this is the third harmonic. If you look at the one above, which harmonic is that going to be? There are 1, 2, 3, 4 bubbles. So it looks like it's going to be the fourth harmonic, right? A first harmonic would literally just be one bubble. A second harmonic would be 2 bubbles, a crest and a trough, and this is our third, this is our fourth. You get the idea. The first harmonic is the lowest frequency that will fit on a pipe or a string. So that's the lowest frequency that would fit on a pipe or string, and that's standing waves. Another example of standing wave is we're really close to Lake Michigan. Every now and then you'll hear of Lake Michigan having a seiche, S-E-I-C-H-E, and it's where there is a standing wave that is set up all across the lake, and you'll get one side of the lake that has a really high tide, for lack of a better word, and the other side of the lake that has a really low tide, again, for lack of a better word, because the wave has pushed that way and created a standing wave in the lake. And the seiche is just another version of a standing wave. All of our instruments, they produce standing waves whenever we look at those. So they each have a certain length that will create a certain length of a harmonic, and that harmonic will let us know whether that sounds good or not, and it gives the different undertones that you would hear in that. So as a whole, that is what waves are. It's some of the different properties of waves, like reflection, refraction, diffraction, standing waves, harmonics, constructive and destructive interference. And then we'll also sprinkle in here, or at the end here, we'll put a video of us doing some of those so you can see on a really big slinky, like the longest slinky you've probably ever seen, some of those examples.
All right, so today here we're going to talk about the 2 types of waves here. They're going to be transverse and longitudinal. So the first type of wave here is actually going to be a transverse wave. So the first actually thing we're going to talk about here is actually going to be the wave propagation. So first of all, this is my voice, coming through the air here. And so, you think that, sound here going through the air, that wave here is going to be, the air would be the medium as the wave. But this time here, as I move the spring, this is actually going to be, the spring here would actually be the medium actually. So a couple of other things here. So if I send just one pulse down, notice that, yes, that's what I'm going to call a pulse, versus a wave, which is going to be, a continuous motion. So a couple other definitions that we're going to apply here. So we're going to actually define here the crest of a wave here as being the highest point of the wave. So in this case here, this is going to be the highest point. That's going to be approximately, at least on my wave here, about 1 tidal away. And the trough then is going to be the lowest point, which is in this case, again, about 1 tidal away here. So the other key feature then is going to be about the wavelength. So that actually is the distance here between 2 consecutive crests or 2 consecutive troughs.
Okay, so remember in that first type of wave, we had the wave going this way, but the spring was going side to side with the slinky. With a longitudinal wave, it works the other way. The wave is going this way, but the slinky particles are also going that way. So if I push it this way, you can see the compressions are where it's pushed together, and the rarefactions then are in the spaces where the molecules are rare or there are less of those molecules. So you have those 2 types of waves, in both cases, notice that the part of the wave, the medium that it's traveling through, it doesn't travel the entire length of the slinky. It either moves side to side while the wave goes that way, or it moves back and forth while the wave goes that way. And that's your two types of waves, transverse waves and longitudinal waves. So the next property we want to talk about is interference, and that's when two waves meet each other or two waves pass through each other. So what we're going to do is I'm going to send a pulse down the slinky this way, where I'm going to move my arm one block to the left here, and Mr. Clamo is going to do the same thing but send his towards me one block this way. So because they're both going to be on the same side, what will happen with the construct of interference is those two amplitudes will add up and it will make the amplitude bigger just for that moment that they're passing through each other, and then my wave will keep going towards Mr. Clamo and his wave will keep coming towards me. That'll be constructive interference. So here we go. 3, 2, 1. 3, 2, 1. 3, 2, 1. Okay, and that is constructive interference.
All right, so now we're going to talk about destructive interference here. So while constructive interference here adds the two amplitudes together, destructive interference here is actually going to subtract the amplitudes together. Notice here that we say this is not going to cancel the waves here, this is just going to subtract the amplitudes. So again here, I'm going to move my wave here to the right, and Mr. Fuelling here is going to move his wave to the right. So, some of the key features here while you're watching this here is you're going to be looking here about 2 tiles away from me here at the center point here to watch how the waves interact with each other. Also, while you're watching this here, think about, are the waves going to be bouncing off each other, or are the waves going to continue on with each other towards, Mr. Fuelling and myself? You may need to rewind to watch the video again here to see how that works. And see how that works so here. Okay? So 3, 2, 1. 3, 2, 1. 3, 2, 1.
Another thing we want to show you is standing wave. And a standing wave is when I send a wave down and that wave reflects back. If I keep doing it to where the wave interacts with itself, notice that I have 2 spots here where there are 2 bubbles. Those are what we would call an antinode. It's where the medium has its maximum displacement. Then there's also a spot in the center where we would call a node, and that's where there is no displacement. Node, no displacement. So there's one there, Mr. Clamo has an end, and technically my end would be a node also. We would then say that this is the second harmonic because it has 2 antinodes. So the number of antinodes that it has tells you which harmonic it is. If we get this going a little bit more, then we can get, let's see if I can get it here. That would be our 3rd harmonic, because you can see the 3 bubbles from that, and then the 2 nodes in the middle and the 2 nodes at the end. And then if we get going into more than that, once you hit it, you can actually feel it in your hands because the wave bounces back at just the right moment. So this looks like it's the 4th harmonic. Now notice too that the higher the harmonics that I have, the more I'm having to move my hand back and forth, the higher that frequency is going to be. And so if we get another set of, another harmonic in there, I can't quite hit that next one there. But you get the idea. So the nodes are the areas where it's not moving. The antinodes are the areas where it is moving the most. And then The standing wave is because it's reflecting back and interfering with itself at a constructive interference at the antinodes and a destructive interference at the nodes.